Hi, my name is Emery Yildirim, a PhD student at the University of Manchester studying materials for fusion energy. It's Friday the 6th of May and this is your Fusion News Update. Today's stories include 1. HB11 awarded $22 million project to develop Australian nuclear fusion industry. 2. White House sets sights on commercial fusion energy. 3. Machine learning harnessed to extreme computing aids fusion energy development. And 4. Princeton physicists unravel a puzzle to speed fusion energy development.
And there are some bonuses for you at the end too.
1. HB11 awarded $22 million project to develop Australian nuclear fusion industry. Our first story today is all about HB11, an Australian nuclear fusion company. Now, they're looking at doing hydrogen boron fusion, and they've just been awarded $22 million in order to develop a petawatt laser that can aid the fusion of these fuels. And this is part of the Trailblazer grant awarded to the University of Adelaide and the University of South Wales. HB11 seeks to use proton and boron fuels instead of the classic deuterium and tritium due to the abundant nature of both sources and that it is aneutronic, meaning no neutrons are produced. These neutrons go on to cause damage to surrounding materials and cause the production of radioactive waste. The petawatt laser they will be building will be used to heat these fuels in order to produce fusion. Now, to put into context just how much power a petawatt laser needs, your microwave at home probably does 900 megawatts, then your local power station is probably pumping out gigawatts. Now, this is 1,000,000 times more than that, so it's a serious task, but it's a seriously important one if you want to get to the kind of temperatures required for proton boron fusion. 2. White House sets sights on commercial fusion energy. Last month, as reported in one of our previous Fusion News episodes, the White House convened a summit in order to discuss the development of fusion energy all across America. Now, recently, the American Institute of Physics has digged a little bit deeper into what was said and what this means for fusion energy development, with private investment pouring into companies in the States. The current administration have not managed to back up their rhetoric about fusion with the kind of funding required in order to match some of these policies. At the summit, discussion was focused around technical hurdles to the fusion industry and promoting a strategy to overcome these, where they announced an agency-wide initiative at the development of a decadal strategy to accelerate the viability of commercial fusion energy. Some of the fusion experts present were excited about the progress fusion is making and were supportive of the new strategy. Princeton Plasma Physics Laboratory Director Stephen Cowley said, "2021 was an amazing year for fusion. I don't think we've had a year like this ever in the history of fusion." Livermore Lab Director Kim Boodle said, "We used to always say fusion energy was 50 years away from whatever day you asked, and I would say that we're closing that gap fast. As the US and the world start thinking about net zero energy, fusion energy has a real potential to contribute." FIA companies and leadership were key participants in the event, this demonstrating the fact that the private sector is going to be leading the way in commercializing fusion energy. It's really great to see fusion right in the minds of the current administration, and we hope to see America back in fusion technology as a whole, as we've seen how successful that has been with other technologies in the past. 3. Machine learning harnessed to extreme computing aids fusion energy development. Now, many of our previous episodes have discussed harnessing machine learning and other fast-paced algorithms in order to predict the goings-on of the fusion plasma. Now, how do we know those predictions are correct? And there's two ways we can do that. Our first way is to look at the plasma and observe experimentally all the goings on, but usually we can't get a really accurate and highly spatially resolved picture of the plasma. So our other way we do it is by using fundamental physics equations and solving them, but these are usually really big and really computationally intensive. The first principle calculations usually take a really long time to do due to the many variables that need to be solved, and we usually make assumptions in order to speed these up. But researchers at MIT have solved one of the most demanding calculations in fusion science, predicting the density and the temperature of a turbulent plasma. Solving this by brute force is beyond current supercomputers, but optimization using machine learning reduced the CPU time to just 8 million CPU hours, which is still an extraordinary amount. This new code will give a really good basis to compare some of our less demanding codes with Professor Jonathan Citroen of Eindhoven University of Technology and leader of the Fusion Modeling Group at DIFA, the Dutch Institute for Fundamental Energy Research, commenting, The work significantly accelerates our capabilities in more routinely performing ultra-high fidelity tokamak scenario prediction. This algorithm can help provide the ultimate validation test of machine design or scenario optimization carried out with faster, more reduced modeling and greatly increasing our confidence in the outcomes. A great step in order to achieve better predictions and a more stable plasma.
And 4.
Princeton physicists unravel a puzzle to speed fusion energy development. Another computational success here, with physicists at Princeton Plasma Physics Laboratory managing to develop a really efficient computer algorithm to model how electrons move in the plasma. Now, plasma is a really hot charged gas that's made up of ions and freely moving electrons. Now, these electrons are really hard to model because they're light and they move really fast. Lead author Yi-Chen Fu and the rest of the team managed to predict the probability of electrons in the plasma taking certain paths and therefore their likely location. Knowing where they might be enables improved use of a common method for stabilizing and heating the plasma, which is passing a current through it. Previously, there's been no working algorithm to do this, and researchers have ended up changing up the equation in order to make it simpler for some of our current codes. Now, this new probabilistic method is going to enable better comparison with experimental data, giving them a better theoretical model to work out what's going to be going on in the plasma. Yet another success in the computational science field, and something that's really dominated the fusion field before due to the complex nature of so many of the physics equations that we have to use. Our bonuses today. Here we have a great video by the Financial Times discussing the latest in fusion and giving a nice introduction to some of the most recent goings on in the field. And in addition, a video of former Secretary of the Department of Energy, Ernest Moniz, discussing fusion as a key climate solution with NBC News' Chuck Todd on Meet the Press. Great to see fusion in such big news outlets. Now, our final story is all about a sapphire fiber that has shown great heat and irradiation tolerance that's going to be ideal for optics in fusion. Optics aren't something that make headlines a lot, but a key part of any fusion device is how we observe the plasma, and with such a harsh environment that can prove quite a challenge. That's everything for this week. Thank you so much for watching, and don't forget to like, comment and subscribe. See you next time.